Hello, in this video we're going to go through the main tests that we're going to be covering in this course, or that we have covered in this course, depending on when you watch this video. The whole idea is to give you a better understanding of the differences and the similarities between the different tests. So to start with, we're going to look at the chi-square. The requirements are that they have to be two categorical variables. And by categorical, that means it isn't a scale, it isn't numeric, there's no number that you can really assign to it. So for example, gender and political party. And even though you could say like gender, female 1, male 2, that number has no meaning, which is what makes it categorical. In terms of which one's the independent variable and which one's the dependent variable, it doesn't really matter. It just kind of depends on how you look at the data. For this example, I think gender is related to political party. So gender is the IV, the independent variable, and political party is the DV, the dependent variable. Yet you could easily flip this around and look at it the other way. So the variables here are gender and political party. So you can see gender is a categorical variable with two groups, male and female. And political party is a categorical variable with three groups, Republican, Democrat, and Liberal. Then we've got the two research questions. We've got our null hypothesis, which is this first one, that there is no relationship between gender and political party. And then we have our alternative hypothesis, which is that there is a relationship between gender and political party. So that is the chi-square test. Let's move down to an independent samples t-test. So for the independent samples t-test, you've got one categorical variable that only has two groups. So you can only have two groups and one categorical variable with an independent samples t-test. You then have one scale numeric variable that's your dependent variable. An example of this is gender versus TV watching. So in this example, gender is our categorical variable with two groups, male and female, and TV watching is our scale/numeric variable that is representing numbers of hours a week someone spends watching TV. Our null hypothesis is that there is no significant difference in TV watching based on gender, and our alternative is that there is a significant difference in TV watching based on gender. So in this case, we're just looking at the difference between men and women and their TV watching habits. So very similar to an independent samples t-test is an Anova. And I'm going to go ahead and get this on its own page. So we're not looking at it kind of broken apart. But with the Anova, an Anova is just running multiple independent samples t-tests. So instead of just having it with one categorical variable that has two groups, instead for the Anova, we've got one categorical variable that has three or more groups. So for example, political party, Republican, Democrat, Liberal. And it still has that one scale numeric variable. So in this example, I've got political party versus TV watching. So you can see it's very similar to the independent samples t-test. The only difference is that that categorical variable in an Anova, it has to have three or more groups. For the t-test, you can only have two groups. So depending on if your categorical variable has two groups or three or more, you would do an independent samples t-test or an Anova. So for this example, like I said, political party is just a categorical with three groups, Republican, Democrat, Liberal, where TV watching is our scale numeric variable that includes the numbers of hours a week someone spends watching TV. Our null hypothesis is that there is no significant difference in TV watching based on political party. And our alternative is that there is a significant difference in TV watching based on political party. So those are very similar. So those hypotheses are very similar to the independent samples t-test. Like I said, the only difference is just in that categorical variable. The independent only has two groups and the Anova has three or more. So next, let's move on to the Manova, so multiple Anovas. And the only difference between an Anova and a Manova is that here, instead of just having, we've got that one categorical variable, right, that's got 3 or more groups, but then we've got, for our dependent variable, we've got 2 or more scale numeric variables. So we're doing multiple Anovas here. So we still have just that 3 or more groups. So here we still have political party. So we had political party here. And we still have TV watching. So still TV watching. The only difference is that we now added a third dependent variable, exercise. Now important, this dependent variable has to be scale numeric. So for this example, it's the number of hours a week someone spends exercising. So that is our second dependent variable that is scale/numeric. And that's how we know, I mean, that's what makes the difference between the Anova versus the Manova, is that you have this extra down here, this extra dependent variable. You still have the one categorical variable with 3 or more groups. You've just now bumped it up to one extra dependent variable. So for the null, we've got there is no significant difference in TV watching and exercise based on political party. So in this case, we've got the TV watching and exercise right there. Right, that's our 2 scale variables based on political party. And then we've got there is that significant difference. So that is Anova versus Manova versus independent samples t-test. All right, moving along, let's look at our correlation. So for a correlation, we've got 2 paired scale numeric variables. And what that means by paired is that those 2 scale variables have to be linked in some way. So it can be linked, there just has to be a linking thing. So it could be a person, and for example, their TV watching and their exercise. It could be a state, and let's say the state's COVID rate versus the state's poverty rate. So that pairing is that it's by something, right, is connecting those 2 scale numeric variables. There is no independent or dependent variable. With a correlation, the variables are interchangeable. And I don't know why it doesn't like that word. Oh, maybe it just wants that. Okay. Are interchangeable, and the results are only checking for a relationship. So the strength and direction between the variables. So it doesn't matter what order you use, it's the same thing. So we're going to use TV watching and exercise, which once again are those scale numeric variables, right? So TV watching, scale numeric, number of hours a week someone spends watching TV, and exercise, number of hours a week someone spends exercising. Our null is that there is no relationship between TV watching and exercise, and our alternative is that there is a relationship. Now we can switch the order. It has no value, no meaning. We could say there is no relationship between exercise and TV watching. It's the same thing as saying there is no relationship between TV watching and exercise. Exact same, doesn't matter. Where it does matter though is with the linear regression. So down here we've got our linear regression. Now our linear regression is very similar to a correlation, except in this case, so I mean we're still using our 2 paired scale numeric variables. So in this example, exercise versus TV watching, right? So that's still the same. The only difference is which variable is the independent variable and which is the dependent variable depends on which variable you think predicts the other. So that's the big thing with a linear regression, is that it has to do with prediction and how one variable predicts the other. So in this example, the independent variable is exercise and the dependent variable is TV watching, because we think the amount someone exercises predicts how much TV they watch. And you can see that over here in our null hypothesis. There is no significant prediction of TV watching by exercise. So we don't think exercise can predict TV watching. And then we've got our alternative, that there is a significant prediction of TV watching by exercise. And our type of variable, that stays the same. TV watching is still our scale numeric, and the exercise is still number of hours a week someone spends exercising. So let's compare that then. So we've got, right, we did correlation where it's the same type of variables, but we're just saying we just think there's some kind of relationship and we just want to know the strength and the direction of that relationship. If you move on to the linear regression, in this case what we're talking about is that there is some kind of prediction. We know something is happening, we're just not sure, or we think, right, that one predicts the other. So the correlation is where we don't really know. You know, we aren't saying one predicts the other. That's where you get that whole correlation is not equal to causation, because we don't know if one predicts the other. But with a linear regression, we can say, well, if it's significant, that one variable predicts the other. You can still switch the variables. The only difference is if you switch the variables here, you will get a different answer. If you switch the variables with a correlation, you get the exact same answer. With a linear regression, which variable you think is the independent variable and which you think is the dependent variable will change the outcome. So it's very important that you're specific in terms of, I think this predicts that, and then when you enter it into JASP, that's how you put it. So for this example, once again, it's that there is no significant prediction of TV watching by exercise, and there is a significant prediction of TV watching by exercise. So in this example, the IV is exercise, so the independent variable is exercise, and the dependent variable is TV watching, because we think the amount someone exercises predicts how much TV they watch. Now, once again, we could flip that. We have the type of variables where you could flip those and you could say there is no significant prediction of exercise by TV watching. And in that case, instead, you would think that the DV, dependent variable, is exercise, and you think the amount someone watches TV predicts how much they exercise. So you could flip that. That's fine. It just depends on what you think in terms of which variable predicts the other. Just remember, it is important that how you enter it into JASP will, impact the outcome. So however, whichever one you think is the independent variable, whichever one you think is the dependent variable, make sure that aligns in JASP, because you will get a different outcome if you flip those variables. Okay, so we looked at correlation, right? Doesn't matter the order, we're just looking at strength and direction. Then we look at linear regression, which we can start predicting. And then we're going to look at multiple linear regression. So for this one, we've got 3 or more paired scale numeric variables. So you've got 2 independent variables that you think predict the dependent variable. So once again, this is mix and match. A lot of this just has to do with hopefully the research you've done and the lit review and those types of things. And you're like, okay, based on my research or my knowledge of the subject area, I think these 2 scale numeric variables predict this third. Or, you could have 2, so I've got, in this example, there's 2 IVs, but you could have more. So I guess I'm going to go ahead and I'm going to update this just so it's clear that 3 or more paired scale numeric variables. And that is very important because this is example, I've got 2 independent variables, right? So I've got age and exercise are my independent variables, but I could have age, exercise, weight. I could start throwing in lots of different independent variables that I think all impact how much someone watches TV. So it's not just that you can only have 2 independent variables, but you need at least 2 independent variables that you think predict this one dependent variable, and you only get 1 dependent variable. So which variables are the IV and which are the DV depends on which variables you think predict the other variable. So in this example, the independent variables are exercise and age, and the dependent variable is TV watching because we think someone's age and the amount they spend exercising predicts how much TV they watch. So I think someone's age and how much they exercise predicts how much TV they watch. But you could easily flip that around. You could flip TV. I would not say, and this is where a little bit of intelligence, maybe it could, but I probably wouldn't say I think exercise and TV watching predict age. I mean, maybe you do, but you'd be more likely to think maybe exercise and TV watch. Oh, maybe exercise and TV. Maybe TV watching and age, or age and exercise. But now that I said it, I guess you could flip it around. The biggest thing, though, is it comes down to your educated decision based on your knowledge and your expertise and your research in terms of what variables do you think help predict that one other variable. The other important thing is these do have to be scale numeric variables, right? Number of hours a week someone spends watching TV, number of hours a week someone spends exercising, a person's age in years. That is a number. That is a number that has value. Then our null hypothesis is that there is no significant prediction of TV watching by age and exercise, and then that there is a significant prediction of TV watching by age and exercise. So that ends all of the different tests covered in this course. I hope this helps. And if you have any questions, feel free to reach out and let me know.